Hey everyone, my name is Michael Perinotto. I'm currently a master's student enrolled in the Energy Systems Engineering program here at Lehigh University. My capstone for the fall 2023 semester is about powering the blue economy by utilizing marine energy for coastal and offshore industries. So, what is the blue economy? The blue economy is the sustainable use of ocean resources for economic growth, improved livelihoods, and ocean ecosystem health. Many ocean-based industries are included in the blue economy, such as fishing, trade, offshore oil and gas extraction, offshore renewable energy, and tourism, to name just a few. Due to the increased demand for ocean-based resources like food, materials, and knowledge, along with technological innovations and more efficient practices, the ocean economy is seeing rapid growth. Ocean-based industries contributed over 1.5 trillion USD in value added to the global economy, approximately 2.5% of the global gross value added. This value is increasing and is expected to double by 2030. With the increased demand for and value added by the ocean economy, the United States Water Power Technologies Office created the Powering the Blue Economy Initiative in 2019 with a focus on two market themes. Power at Sea focuses on utilizing marine energy for industries offshore, such as ocean observation and navigation, underwater vehicle charging, seawater mining, offshore marine aquaculture, and algae production. The United States possesses one of the largest exclusive economic zones. However, due to a lack of reliable offshore power in many regions, many of these industries are relatively small or just emerging. Utilizing renewable marine energy would facilitate the emergence and growth of these industries, increasing the value added by the blue economy. The second market theme is resilient coastal communities. Climate change is increasing the rate at which coastal communities are affected by natural disasters. Industries such as desalination, coastal resilience, and disaster recovery were determined to be important for the development to strengthen coastal communities as the impacts of climate change worsen. Isolated and island communities were also investigated by the Water Power Technologies Office to determine how marine energy can improve reliability and resistance in these areas. So, what is marine energy? Well, here's a map that shows the technical power potential of marine energy resources in the United States and territories. As you can guess, marine energy is any form of energy that we derive from the natural movement of water or thermal gradients. Out of the 50 states, the United States has a technical capability of producing 2,300 terawatt hours per year of clean marine energy. Nearly half of this energy can be captured in Alaska alone due to increased wave heights at higher latitudes and extreme tidal currents. There's a distinct difference in marine energy resources between the East Coast and the West Coast. The West Coast technical power potential is 250 terawatt hours per year, with wave energy alone accounting for 96% of this potential. This is due to the size of the Pacific Ocean and the resulting large wave heights. The East Coast technical power potential is 460 terawatt hours per year, with ocean thermal accounting for a majority of this potential, followed by ocean current and wave energy. Currently, there are around 334 marine energy devices that are in development or ready for commercial use. Out of the 334 devices, 25% have a technology readiness level of 7 to 9, 54% have a readiness level of 4 to 6, and 21% have a readiness level of 1 to 3. Due to the design of the technology and geographic location limitations for ocean thermal and ocean currents, my capstone focuses on tidal current energy for resilient coastal communities and wave energy conversion for power at sea. The first side of the blue economy I explored was resilient coastal communities, specifically the desalination industry. I chose desalination due to the projected rise in global freshwater scarcity. Many industries and infrastructures overuse water. Water used for agriculture is often oversupplied due to inefficient processes that cause most of the water to evaporate. Groundwater sources are becoming more contaminated by improper water treatment methods as well. Due to those and other factors, water scarcity is affecting 4 billion people for at least 1 month each year. Climate change will also increase freshwater scarcity due to increased evaporation rates, high volatility of precipitation, and reduced glacier and snow area. Desalination is the process of removing salt from water. There are two primary methods to desalinate water, which are thermal and reverse osmosis desalination. Thermal desalination has been in use much longer, but with innovations in reverse osmosis technology, RO desalination is becoming the most popular option. Between 2000 and 2020, The global capacity of desalination plants increased from 20 million cubic meters to 95 million cubic meters per day. This trend is expected to increase as natural freshwater sources become less available. To put this in perspective, assuming that a reverse osmosis desalination plant is completely supplying an average American household with water, there would be a roughly 10% increase in the household's annual power consumption. However, since most houses are already supplied from other freshwater sources, this percentage would realistically be smaller. To power reverse osmosis desalination plants, I explored how energy can be supplied with an array of tidal turbines. Tidal current turbines capture the kinetic energy from tidal currents, very similar to how wind turbines capture the kinetic energy from wind currents. However, there are a few advantages that tidal energy has over wind energy. For one, the density of salt water is approximately 837 times denser than air. So, even at lower current speeds, the energy density of tidal currents is much larger than that of wind. Tidal currents are also extremely predictable. We have over 150 years worth of tidal data that correlate with the motion of the moon around the Earth. Additionally, NOAA provides a handy tool used to predict tidal currents for any given date in the future. Every day we can rely on there being too high and too low tides. Flood currents peak around the high tide, where the ebb current is at a minimum, and likewise, ebb currents peak around low tide when flood currents are at a minimum. Tidal currents overall are at a minimum in between high and low tides when the flood and ebb currents cancel out. It's important to note that flood current peaks are greater than ebb current peaks. Now, looking at how tidal currents can power reverse osmosis desalination plants, I made a graph comparing the hourly power demand needed to supply 1,000 American homes with desalinated water, with a theoretical output of an array of 20 tidal turbines. The blue line shows the theoretical output of the tidal array located at Hell's Gate in New York City. The equation below shows how that line was calculated. The output of the tidal turbine grows exponentially with the radius of the turbine and the current flow velocity. Power coefficients range depending on the design of the tidal turbine, but typically fall within a range of 40 to 50%. The tidal current speed in Hell's Gate ranges from 0 to around 2 meters per second, and even though this is a relatively small flow velocity, the high energy density of seawater increases the output significantly. Tidal turbines typically have a cut-in speed of 30% of the turbine's rated speed. I modeled the turbines with a rated speed of 2.5 meters per second, which corresponds to a cut-in speed of 0.75 meters per second, which does not affect the power output significantly. The geographic location of the tidal site determines the size of the turbine geometry and array size. Channeled width and height limit the size of the turbine to prevent water turbulence from affecting downstream environments. Furthermore, if vessels are navigating over the turbine array, a clearance of 5 meters is needed for small vessels and 20 meters for large seafaring vessels from the surface of the water. Hell's Gate has a depth of 10 meters, and the only vessels that navigate over the channel are ferries or small boats. So, to meet the clearance requirement, the turbines were designed to have a cross-sectional radius of 2.5 meters. Looking at the graph, we can see the four peaks mentioned last slide. The first peak and the second peak correspond to the first low and high tide for that day. Both peaks exceeded the power demand for the desalination plant. The third peak is the second low tide and just barely meets the power demand. The fourth peak is the second high tide, and since it occurs during the night, the power supplied is much greater than the demand. Overall, I found that tidal energy powering reverse osmosis power desalination plants can supply fresh water to coastal and island communities. With the extreme predictability of tidal currents, communities served by RO desalination plants can see an increase in freshwater reliability and resilience. However, for this capability to be fully realized, energy or water storage is necessary for when the tidal array supplies more power than needed for periods when the tidal array output is smaller than the demand. Or, depending on the size of the community's water demand, excess power generated by the tidal array can be supplied to the local grid. Now, looking at the second side of the blue economy, power at sea, I chose to explore the ocean observation navigation industry. I chose the ocean observation navigation industry for two primary reasons. First off, the market value of the ocean observation navigation technology is rising as more technological innovations emerge. The emergence of greater technological innovations is creating a greater demand for ocean knowledge. The sale of ocean observation navigation equipment more than doubled from 2001 to 2011 from 7.5 billion to 16 billion USD. This trend is expected to increase as new technologies are implemented on ocean platforms. The second reason was that even though there were technological innovations, most of the innovations focus on minimization and increasing the energy efficiencies of devices currently deployed on buoys. This is because buoys currently operate to minimize power consumption since most are powered by batteries or solar PV panels. The Dart 2 buoy shown on the left is used to detect early signs of tsunami activity and is powered by around 6 kilowatt hours of alkaline D-cell batteries. To limit power consumption, data collected on sea heights is collected 24 times in 15-minute intervals once every 6 hours. The Scoop data buoy, shown on the right, is a modular buoy powered by 200 watts of solar PV panels and a 1.34 kilowatt hour battery. The solar PV panels provide a more consistent energy supply, which increases the data continuity and reduces maintenance costs. However, this limits the range of deployment at higher latitudes and comes with periods of intermittency depending on weather conditions. Some buoys are cable to shore, but this increases the costs and limits the range of deployment. Wave energy may be the answer to the power supply problem due to the high energy density of seawater and the constant motion of the ocean surface. By optimizing capital costs of buoy technology, energy storage, and wave energy converter installation, along with optimizing operation costs of battery replacements, wave energy converter maintenance, and vessel operations, it is estimated that around 0.5 to 3 kilowatts of wave energy converters and 15 to 50 kilowatt hours of battery storage provide one of the most cost-effective options for the lifetime deployment of current and emerging ocean observation and navigation technology. So, what is wave energy and how do we harness it? Waves are caused by the friction of wind across the ocean surface. Due to the wide surface area of the oceans, wind is always blowing at some point, meaning the surface of the ocean is constantly moving. The height and period of waves vary from day to day, but looking more broadly, there are some common trends. Wave energy is greater at higher latitudes, as shown in the image, and peaks during the winter, where colder air transfers more energy to the relatively warmer ocean water. Additionally, wave energy is greater the further offshore due to less drag between the wave and the ocean floor. Wave energy converters capture the energy held by ocean waves in a wide variety of ways. Overall, there are 4 main categories of wave energy converters that capture energy from the different types of wave motions. Heaving devices capture the energy from the vertical heaving motion of ocean waves. The GIF on the left side shows a linear absorber. Linear absorbers float on the ocean surface parallel to the direction of the wave. The GIF on the right side shows a point absorber that captures energy from 6 degrees of motion. Heaving devices generate energy by moving a shaft vertically along a non-moving submerged body, converting linear motion into angular motion that can power a generator. Heaving devices can be either anchored to the seafloor or float with mooring techniques. These devices are one of the best options to use for the ocean observation and navigation industry, since sensors can be housed in the floating body on the surface and batteries can be stored within the spar. Looking at the right side shows an oscillating wave surge converter. This type of device converts energy from the oscillating horizontal motion of waves. Connected to the flap would be a hydraulic system connected to a generator. These devices are more efficient closer to the coast and fixed to the seafloor at depths of 10 to 50 meters. However, they can be located further offshore with mooring techniques. The 2 other categories of wave energy converters utilize turbines as a main power transfer mechanism. The GIF on the left shows an oscillating water column. Oscillating water columns capture energy by allowing waves to increase or decrease the air pressure in a chamber. As water rises in the chamber, air pressure increases, in turn pushing the air out through a turbine along the top of the chamber. As the water recedes, pressure is reduced in the chamber, drawing air back in and turning the turbine again. Overtopping devices allow waves to overtop the device to capture the potential energy of the water as it drains through a turbine on the bottom of the device and flows back out to sea. These devices are typically large in scale and more oriented to supply grid-scale electricity. Since these devices produce way more power than needed for ocean observation and navigation buoys, they're left out of the analysis, but will be of great importance for next semester's Capstone. Both of these devices can be located on the coast, anchored to the seafloor, or floating with mooring techniques. So, how do we know how much power can be extracted from the ocean waves? Well, for every wave energy converter that I just covered, The amount of extracted power is dependent on the capture width, wave energy density, and capture width ratio. The wave energy density for a particular area is determined by the average wave height and period of the wave. It is also multiplied by the density of seawater times gravity squared over 64 pi, which is roughly around 0.5 kilowatts per cubic meter seconds. Wave power density can be numerically calculated in areas where data buoys are deployed. However, NREL provides an interactive map that measures the average monthly wave energy density within the United States exclusive economic zone. The capture width ratio is the percentage of energy extracted from the ocean wave. For a particular device, capture width ratios are determined through modeling and testing due to the wide variety of wave energy converter designs utilizing different power transfer mechanisms. Capture widths also vary among devices, with heating devices typically having the smallest capture widths, followed by floating oscillating wave surge converters and oscillating water columns. Even though there isn't a great correlation, the capture width ratio typically grows with capture width. The graph on the right shows the power output of the three devices just mentioned 50 nautical miles offshore Newport, Oregon. A great paper created a database of over 100 wave energy converters that found the average capture width and capture width ratios of each device. Using this data and the equation shown, the average power output was found for each device, and the winter peaks can be seen at the end of the graph. Now that we know the power demand and supply, we can make some conclusions. As we saw on the last graph, the average power output of wave energy converters are much higher than the optimal power requirements for the ONN technologies. Wave energy converters must be scaled down to have capture widths of around 1 to 4 meters. Scaling these devices down would produce an average of 3 kilowatts during the summer minimum and 60 to 7 kilowatts during the winter peaks. Shown in the image is the Ocean Power Technologies power buoy. It is a perfect example of a wave energy converter paired with ocean observation and navigation technology. It is a floating point absorber with sensor technologies located within the float, while batteries are located within the spar along with the generator. It can continuously power onboard devices such as high-definition cameras, a 5,000-meter warning sensor, and other data sensor technologies. If there is an array of power buoys in a region, they can all be connected to an undersea substation capable of supplying power at sea for other offshore industries or supplying power to the coastal communities. Due to the continuous power granted by wave energy converters, this increases the amount of data collected along with its continuity. And since the batteries don't have to be manually recharged, these types of battery buoys require much less maintenance, reducing overall operational costs. Due to the unique marine energy resources that the ocean provides, this type of energy generation allows for more consistent, predictable power compared to other renewable resources. With predictable tidal energy powering reverse osmosis desalination plants, a predictable freshwater supply can be established, increasing freshwater resiliency and reliability. And due to the constant motion and high power density of ocean waves, wave energy converters offer a more consistent and reliable power supply to offshore industries and coastal communities. This capstone was essentially a feasibility analysis of marine energy applications for the blue economy. Next semester, I will be exploring how to combine these sources of energy, along with energy storage solutions, to power a wider array of industries within the blue economy. After optimal energy generation and storage techniques are established, I will be conducting a techno-economic analysis to determine the feasibility of these energy systems. Overall, by utilizing green renewable marine energy resources for applications in the blue economy will help facilitate a green energy future. Thank you for listening, and if you have any questions, feel free to email me at mapf23@lehigh.edu.